All right, so going back, sometimes I get students who ask me, should I memorize it? No, don't memorize each individual. But what you try to do is you try to memorize the patterns. That's all. We always try to memorize patterns. Not, because patterns are much more useful than memorizing individual entries. Because when you memorize individual entries and you just have that, then you can't go beyond that. Whereas patterns, you can at least extrapolate patterns out and try to figure out. But but finding these patterns is, the best way of finding patterns is if you find them, because then you have a better idea of how good that pattern is. If somebody just told you, okay, this is the pattern, memorize it, you don't know, what that pattern is based on sometimes. You don't know how much data. If somebody just told you the average bond length is this, well, how many data points went into the average? Hundreds, thousands, or only one? What's the range? That kind of thing. And so in science, we try, we try to quantify these types of things mathematically. And one of the things we use to quantify these things is called the standard deviation. Or in science, we typically use what's called if we have an infinite data set, it would be 1.95 times the standard deviation, or what we call the 95% confidence interval. Looking at statistics and understanding these things statistically. But anyway, we're going to talk about statistics later. But you kind of see the pattern, you get an idea, for certain things. Anyway, you want some kind of take-home message for what we were talking about, the Chem effect over here, and so sometimes I won't give you the take-home message. It's best if you figure it out yourself. All right. Well, why are we talking about acids? Well, the reason we're talking about acids is this. Going back to the original reaction, which seems long ago, but we have no driving force here. Because when I do double replacement reactions, I look for three things. I look for precipitation, no precipitate. I look for going from a stronger acid to a weaker acid, because that's going from something less stable to something more stable. Now, a lot of people recognize this as water formation. Well, water usually forms from things that are less stable. And so that often works for Chem 4. But rather than saying water formation, just go stronger acid to weaker acid, because water is not the weakest acid on the chart. Actually, you probably is water the weakest acid on the chart? No, and so if you were to form one even weaker acid, you potentially miss that reaction. And so stronger acid to weaker acid. And gas formers, which we'll talk about in a minute. But basically, there's no reaction here. And so there's no driving force. No reaction. And so we just like to show it, and so if you just write NR here, like this on a test, and you were wrong, you lose a lot of points. But if you write NR like this and you show it, and I see why you're arguing for no reaction, then you get a lot more points. You get a lot more partial points. There's a lot of people just like to cut it off here and not show this. But silver chloride and HNO3, I know this reaction very well, because when I was taking Chem 1B, we had a challenge in our class, and each person was supposed to take silver chloride and convert it into silver nitrate. So how do you take silver chloride and convert it into silver nitrate? Well, you can't just react it with nitric acid. And so I was stumped. I didn't know. Silver chloride's insoluble. So how can I get it to react? I was stumped. Well, it turns out, I had all this stuff memorized, but I was in a kind of a narrow window. I didn't know, that things can change depending on conditions. And so it turned out the answer was you don't use 1 molar nitric acid, And you don't do it at room temperature or around room temperature. Instead, what you do is you use hot concentrated nitric acid, like 16 molar. And you take hot concentrated nitric acid, it'll dissolve, eat up the silver chloride. It forms this, but even this is incorrect. Can you put plus, etc.? It's silver nitrate plus HCl plus etc. Because this is, in fact, I need to fix this slide. I forgot to. Semester. The nitric acid is kind of a special acid. You got to do this in the hood, and I don't know why I didn't fix this one this time. I've been using these for years. That's a little different reaction, but yeah. Hot, concentrated, and it dissolves, to form silver nitrate plus, etc. Things like, we're going to form NO plus NO2, etc. We'll talk more about this type of reaction later. This is a redox reaction, actually, not a double reaction. All right, continuing on, lead 2 nitrate plus sodium hydroxide. This is a reaction that was done in Chem 1A. Have you seen this? When you take lead 2 nitrate plus sodium hydroxide, you form a white PBT of lead 2 hydroxide. But if you add too much hydroxide, that white PBT disappears. And so the white PBT gets converted into this. This is called trihydroxyl plumbate ion. And this is an example of what we call complex ion. We have too many hydroxides stuck on there, but they get stuck. This is actually what we're going to talk about in the next section. And so the basic assumptions are this. We're working under standard thermodynamic conditions, and we're only looking at the thermodynamic driving force. To properly predict reactions, we must understand kinetics as well. Kinetics is the speed of the reaction. Do you know what's more stable, graphite or diamond? What's more stable thermodynamically? Graphite or diamond? It turns out that graphite is more stable than diamond. And well, if that's the case, then diamond should decompose into graphite because graphite's the more stable form of carbon. But kinetically, this is not going to happen because it would take way too long. And so what we call this is graphite is more thermodynamically stable, and therefore diamond is unstable. But diamond's not really unstable, so we call diamond metastable. Metastable meaning it's thermodynamically unstable, but kinetically stable. The reaction would take forever for diamonds to decompose, and therefore we don't worry about it. There's other examples of this. If I fill in, if I fill this room up with methane, I fill the room up with methane, is that a thermodynamically stable mixture or an unstable mixture? Methane and air. Would you feel comfortable if I filled this room up with methane? I mean, it's smell, but would you feel comfortable? You would feel very uncomfortable because it is thermodynamically unstable. And all it would take is a hot surface or spark or flame, and we could have a explosion or fire, right? But why don't I see an explosion or fire right now? Because at room temperature, this is what I call metastable. I'm not going to see an explosion or fire right now because it's a metastable mixture. I have to increase the temperature a little bit to see that. And so that's another example of metastability. And so sometimes you'll predict a reaction, but nothing happened. Does it look like anything happened? You know, I predict methane will combust in a flame with O2, but do you see it? You don't see it because it's happening so slow, right? If it happened quicker, you'd see it. And to happen quicker, we just need the elevator thing. So just to review, these are the, for metathesis, which are double replacement. Essentially, this is what metathesis means. Why do I call it metathesis? I call it metathesis because not everything fits the AB plus CD pattern. Metathesis is AB plus CD, right? And so rather than calling it, double replacement is AB plus CD. And so I'm going to replace the term double replacement with metathesis. And what metathesis is a favorable ion combination. It doesn't matter how many ions you have. You could have thousands of ions, and you're looking for the ions that like each other, that want to combine. The ions that like each other and want to combine will form precipitates, they'll form gases, they'll form weaker acids. Those are ion combinations. But these favorable ion combinations can be tricky because of things like ammonia. You know, is ammonia an ion or a molecule? Ammonia is a molecular compound. It's not an ion. But ammonia can form ions. We'll talk about that because ammonia is a weak base. Weak bases do what in water? Do weak bases in water partially ionize or partially hydrolyze in water? They do. Well, let me just show you what weak acids do. If I have something like acetic acid and water, acetic acid and water aren't going to go 100% to hydronium and acetate. In fact, we could show this different ways. We could show that it stays mostly as acetic acid and water molecules, and very little of it forms these ions. This is a weak electrolyte. In fact, it stays like 99.9% unreacted, and only about 0.1% reaction here actually occurs. This is weak acid, right? What about weak bases? Weak bases are weak electrolytes. Weak electrolytes do what? Weak electrolytes partially ionize or partially hydrolyze. What's the difference between ionize and hydrolyze? Well, the difference is this is called hydrolysis. This would be ionization. And so if we had partial ionization, we'd show the exact same kind of deal, except we would show it like this. This is ionization, this is hydrolysis. But in fact, they're the same thing for the acids, you know, ionize, hydrolyze, you know. In Chem 1A, I always prefer this. I don't like to write hydronium because we know, do protons, are they stable in water or do they react with water? Protons will react with water to form hydronium. So we aren't going to see free protons in water. We see hydronium. So this is kind of the shorthand way. These two equations mean the same thing. This is just the shorthand way of writing this. This is longhand. But for bases, it's different. For bases, this is the hydrolysis. And so for base hydrolysis, we go like this. You know, acids are proton donors or proton acceptors? Acids. Proton donors. Bases are proton acceptors. And so ammonia is a base. Water is what we call amphoteric. Water can either act as an acid or a base, either way. And so if ammonia is the base, it's going to donate the proton or accept the proton. It's going to accept the proton from the acid water in this case. This is the acid here, this would be the base here. This is an acid-base reaction as well. And so what's going to form? tell me what forms from this proton transfer. Acid-base, we're on acid-base reactions, proton transfer reactions. Acid loses a proton, base gains a proton, what forms? Okay, we're going to get ammonium, NH4 plus, versus ammonia and hydroxide. We know it's a weak base, therefore it only partially hydrolyzes. So most of it will stay as ammonia and water, right? Molecules, and very little of it will hydrolyze. In fact, 99.9% stays as molecules, only about 0.1% hydrolyzes. About. Okay, what's the ionization reaction going to look like? How does ammonia ionize? This is what I see all the time. I see people ionize ammonia like this, H plus plus NH2 minus. They're going to form a proton, and do you know what the name of NH2 minus is? You probably don't know the name because you only saw it once, right? You need to see it more than once to remember the name. What's the name of NH2 minus? Amide. So we form proton and amide. Does this look the same as that? No, totally different. I mean, amide is a way more powerful base than hydroxide. And over here we're forming ammonium. Ammonium is a very weak acid compared to H+. Totally different species. This would be the ranking for ammonium. H+ is the same as hydronium. And so, totally different products. And so, weak bases do not ionize. Weak bases do not ionize. Weak bases, in fact, all bases. The take-home message here is that bases do not hydrolyze. Oh, no, that's wrong. Bases do hydrolyze. The take-home message is what? Bases do not ionize, except for the hydroxides. Like sodium hydroxide will ionize. But sodium hydroxide is tricky because I don't consider sodium hydroxide necessarily as a base. I consider hydroxide as the base. Now, hydroxide, is that going to ionize? Because when I look at my acid-base chart, I'll see hydroxide there. No, I consider sodium hydroxide as a soluble salt, and hydroxide's the base. Does that make sense so far? A little bit? But, you know, what we do is we just keep repeatedly doing this, so eventually it just sinks in. All right, in chapter 3, was it chapter 3? Yes, it was chapter 3. In chapter 3, you discussed organic compounds, right? What functional groups do you recall from organic? Probably the hydrocarbons and the alcohols, or the, you know, hydrocarbons, you have the alkanes, alkenes, and alkynes. The alcohols, right? The carboxylic acids. Did you cover the amines? The amines. Okay. Amines are another category of organic functional group. And the amines are like this. They have a nitrogen, and you're going to have 3 other groups attached. We'll call it R prime, R double prime, R triple prime. This is just the rest. This is where R is either equal to hydrogen or carbon. Do you know the electronegativity of hydrogen? Probably not. 2.1. Do you know the electronegativity of carbon? 2.4. And so hydrogen and carbon's electronegativity are comparable. 2.1 and 2.4 is not the big difference. They're very similar in terms of electronegativity. And so if I have a hydrogen or carbon attached to the nitrogen, it doesn't change the electronic environment around nitrogen very much. And so if I have something like ammonia versus trimethylamine, trimethylamine is going to have 3 methyl groups attached to the nitrogen. Then as far as base properties go, these two are very close in terms of base strength. And so what does trimethylamine do? Well, trimethylamine will hydrolyze water just like ammonia hydrolyzes water. But instead of forming ammonium, it's going to form trimethyl ammonium ion. And a trimethyl ammonium ion just would look like this. And so if I have like something like trimethylamine, I could write it like something like this: NCH3, something like this, plus water. This is going to form trimethyl ammonium, which would be HNCH3. Now it's going to have a positive charge here, plus hydroxide. And so, well, it's a weak base, so it's just partially hydrolyzed in water. But weak bases will produce varying amounts of hydroxide depending on the strength. The stronger the weak base, the more hydroxide they produce. The weaker the weak base, the less hydroxide they produce. And so amines, I can put ethyl groups, propyl groups, whatever, on here, isopropyl, or whatever. I could put a whole bunch of, different groups on here. They're still going to behave like ammonia. And so this is what we mean by ammonia-like compounds. Ammonia-like compounds are the amines. Are amides? No, amides are not. Is this an amine? NF3. Is that an amine? No, because now I have a fluorine attached. Having a fluorine's much, much more electronegative than carbon and hydrogen. This is going to change it. This does not behave as a base at all, an F3. At all. Okay. So, it's mixed up, but let's look first at the driving forces. Precipitation. Here, go back to chapter 5. Actually, I don't like the solubility rules in chapter 5. I like the solubility rules in the Chem 1A lab manual. The solubility rules in the Chem 1A lab manual go like this. And I'm just going to say them. The solubility rules for ionic compounds. This is for ionic compound. Group 1 and ammonium compounds are all soluble. So the first thing we look at is we look at the cation. If the cation is group 1 or ammonium, it's soluble. Then we look at the anions. This is the hassle looking at the cation. We switch to the anions and we go nitrates, chlorates, and acetates are all soluble. Then we go to chlorides, bromides, and iodides. Chlorides, bromides, and iodides are all soluble except for silver, lead 2, and mercury 1. And then we go to sulfates. Sulfates are all soluble except for silver, lead, mercury, calcium, strontium, and barium. Okay, then we switch gears and go to the insoluble anions. The insoluble anions, we start off with, which one do we start off with? Hydroxides? Hydroxides are all soluble. Oh no, that's wrong. Hydroxides are all insoluble, right? Insoluble except for group 1, calcium, strontium, and barium. And then we would go to sulfides. Sulfides are all insoluble except for group 1 and group 2. And then we go to carbonates, phosphates, and chromates, which are all insoluble except for the earlier ones, group 1 and ammonium. Group 1 and ammonium are all And so looking at it, we just say all insoluble, because we look at the cation first if we do it in that sequence. Anyway, go back to the lab manual and just fill out the table here. Just memorize it if you've forgotten it. Did you guys have to memorize it in Chem 1A? Yes? Okay, so it shouldn't be too hard to remember. So that's why I didn't write them down. This you do not have to memorize. You don't even have to look for patterns yet. We'll look for patterns later. All you have to do is use this table. But the one caveat in using this table is the leveling effect. You know, we have to be careful about the leveling effect. But otherwise, it's very simple to use. You know, the stronger the acid here, the higher up it is, and then we have the conjugate bases over here. The stronger the conjugate base, the lower down it is. Then you could read these. Do you ever read these little footnotes here? A lot of people don't, but you should read all the captions and the footnotes. A lot of information. The one thing is, we have different kinds of acids. Do you know how many different kinds? I don't know. Did you guys talk about acids in Chem 1A? You're supposed to cover a little bit of chapter 16, the definition of acids, the 3 definitions of an acid. We have the Arrhenius definition, the Bronsted definition, and the Lewis definition. Well, this table is only good for Bronsted. Lewis is way more complicated. Gas formers. Do you guys remember this? Carbonic acid is inherently unstable. Carbonic acid, if you ever form this, it doesn't last. It decomposes into water and CO2. And so the best thing is don't even write carbonic acid, just write water and CO2. H2O liquid and CO2 gas. Sulfurous acid is inherently unstable. Sulfurous acid automatically decomposes into water and SO2 gas. Ammonium hydroxide, the same thing. Don't write ammonium hydroxide as a product. Make sure you replace it with ammonia and water. H2S is fine. H2S is stable. And so if you generate H2S in a metathesis reaction, this is why people say never mix acid with a sulfide salt. If you mix acid with a sulfide salt or mineral, you're going to be asking for trouble because you're going to generate H2S gas. The good thing about H2S gas is you can detect it at the part per billion level. It has a rotten egg odor. You can smell it. The bad thing about H2S gas is it fatigues your olfactory sensors or whatever, and once they're fatigued, you can't smell it anymore. And so you could be exposing yourself to H2S poisonous gas and not even know it because you can't smell it. And recently, somebody in Ventura, at the one of the oil wells, died from H2S exposure. It's lethal at the part per billion level. Don't mix cyanide-containing materials with acid because H plus likes cyanide to form hydrogen cyanide. Bitter almond, highly toxic gas. So let's look at some examples of metathesis. When we do metathesis reactions, I'd like you to write 3 equations and also show me the driving force. The 3 equations would be the CE, which I use as complete equation, IE for the ionic equation, NIE for the net ionic equation. And so let's look at this one, calcium carbonate and sulfuric acid first. Let's do this as an example. Metathesis reaction. So like I said, metathesis is essentially double replacement. So if it's a double replacement form, just leave it. It's easy. Double replacement AB plus CD. So calcium carbonate, what's the formula for calcium carbonate? CaCO3. I don't want to see these. Don't show me the charges because you could use the charges to figure out the ratios of ions, but leave them off. Leave the actual equation clean. Plus sulfuric acid formula. H2SO4. What's the state of calcium carbonate? Solid, liquid, gas, AQ. Well, solid. Is it soluble in water? Is calcium carbonate insoluble or soluble? Well, carbonates are, well, phosphates, carbonates, and chromates are all insoluble unless it's group 1 or ammonium. So this is insoluble. So even though sulfuric acid has water, this doesn't dissolve. In order to get this in water, you got to attack it chemically. H2SO4 is AQ. What does this form? So we're going to have calcium with sulfate and hydrogen ions with carbonate. And we're going to go to complete reaction. And so calcium with sulfate is just going to form CaSO4. And then hydrogen with carbonate can form bicarbonate or carbonic acid, H2CO3. When we do metathesis, we go complete. And so metathesis, assume complete reaction. Assume complete reaction for metathesis. So we're going to just add the second proton. The carbonic acid is a diprotic acid, right? We'll just add it. But we know something about carbonic acid. Is carbonic acid stable? No, so you know what? I don't want to write carbonic acid here. I'm going to actually exit out and then instead write what? Water, H2O liquid plus CO2 gas. All right, those are my potential products. So my potential products are calcium sulfate and water and CO2. Is this balanced? This is balanced, but before I balance it, I usually look for a driving force, because if there's no driving force, then there's no reason to balance it, because no reaction is going to happen anyway, right? And so what is the driving force? Well, one, we look for precipitation. Is there precipitation? Well, sulfates are all soluble except for silver, lead, mercury, calcium, strontium, barium. Well, calcium is an exception, so it's a precipitate. So would you call this reaction a precipitation reaction? No, because this is a very tricky one. Because what did we start off with? A solid. So we're sacrificing one solid for another solid. Most of the precipitation reactions you saw, and in fact all the precipitation, well, I don't know what your Chem 1A instructor did. Usually in Chem 1A, I try to make it more difficult than Chem 4. So in Chem 4, you're never given a scenario like this. In Chem 4, you're always given aqueous to solid, right? And then in Chem 1A, I try to make it a level harder. You're given solid aqueous forming a solid. So think about this. Think about a reaction as a struggle between the forward reaction and the reverse reaction. Who wins? If we go backwards here and the products actually re-react to form calcium carbonate, we're doing a precipitation reaction in the backwards direction. If we go forwards here, we're doing a precipitation reaction in the forward direction. So you can't say, you know, one direction is precipitation, the other direction is precipitation. Is that the leveling effect for precipitation? Is there such thing as the leveling effect for precipitation? You know, we got precipitation in forward, precipitation in backwards, so therefore they cancel each other out. Is that the case? No, that's not the case. For this, in order to figure out if this is a driving force, we have to see which precipitate is more stable. Is calcium carbonate a more stable precipitate, or is calcium sulfate a more stable precipitate? Because you got precipitate versus precipitate, right? And so which of these two precipitate, I mean, if you're going backwards or forward, which is more stable? And so do you want to just Google it? No, you probably don't want to, and probably doesn't even, if you Google it, you probably aren't going to find somebody answering that direct question. And so what other clues will give you an idea of which one's more stable?
Well, the SO4, like, as its own ion, is more heavily electronegative, so
Well, you guys have to get rid of this electronegativity thing. What makes SO4 more electronegative than CO3? Electronegativity is the ability to attract electrons. Why is SO4 2 minus more attractive for electrons than CO3 2 minus? They have the same overall charge. We have to look deeper into the structure. There is a difference. But let me ask you this question. This is a very common question. Which one is more electronegative? Cl or Cl minus? Are they the same electronegativity or are they different? They're different. Cl minus is not electron. Cl minus hates an extra electron. It absolutely hates an extra electron because that extra electron will go into the next shell, making it very unstable. Cl minus does not want another electron. Cl would love another electron. Well, it doesn't love it, but it can accommodate an extra electron, right? In fact, it does actually. It has a high, what do we call that? Love for electron. It has, in fact, Cl has the highest electron affinity in the periodic table, right? But Cl minus, no way. And so the electronegativities change depending on the structure. If you want to compare electronegativities, you have to look at the structure. You can't just say, oh, Cl is more electronegative than O. Well, if we're talking about O versus Cl minus, then no, O is more electronegative. O is going to have a higher electron affinity. We got to put things in context of structure and composition. Just memorizing a certain number doesn't quite do it, and so we have to look at things in more depth and detail to figure that out. And so the electronegative, it's not the electronegative, but you're getting closer. Do you guys remember lattice energies? What makes a strong lattice? What makes a weak lattice? What has high lattice energies? Really high lattice energies. What has kind of weak or low lattice energies? You've probably done the Born-Haber cycle, where you add up all the numbers and calculate the lattice. You might have done that in a homework problem or in class, right? But did you get any kind of take-home message about lattice energies? Like any kind of pattern that you might have seen? These types of things have high, these types of things have low. Oh, what do lattice energies impact? What is lattice energy anyway? Tell me what a lattice. Well, let's go back to what is a lattice energy. What is a lattice? How about that? Yeah, it's how it's bonded. A crystal's bonded in 3 dimensions. Builds up a lattice, 3-dimensional lattice. The bonding arrangement there. Since there's not just one bond, let me ask you this. In a mole of sodium chloride, solid, how many bonds do I have? In 1 mole of sodium chloride, I have 1 mole of bonds. True or false? In 1 mole of sodium chloride, I have 1 mole of sodium chloride bonds. True or false? Well, what would your first guess be? Just tell me your gut reaction, your first guess. Would be true or false? True? True? False. False. It's false because we got to think in terms of lattice, right? In 1 mole of sodium chloride, there just isn't 1 bond. There are, in fact, each sodium ion in the lattice is bonded to 6 chlorides directly. 4 in the plane, 1 on top, 1 underneath. There's 6, and then indirectly it's bonded to, this is going to be repulsion, but indirectly it's bonded. This we even consider a bond because it's an attraction. Ionic bonds are just attractions between opposite charges. And so this would be a direct bond here. This would be an indirect to the next nearest neighbor, and it goes on and on. And so the lattice energy, the take-home point from the lattice energy is you have a lattice of bonds. What is a lattice of bonds? A lattice of bonds is not just one formula unit, not just one. It's this whole three-dimensional bonding network in which you're going to have, in sodium chloride, you're going to have, in gold, you know how many bonds? In gold, each gold atom is bonded to how many other gold atoms? In 1 mole of gold, in a 1 mole of gold crystal, how many bonds are there? This one is a little easier, maybe. But in gold, there are going to be, each gold atom is bonded directly to 12 other in a metallic bonding arrangement. Metallic bonding is probably best explained using MO theory. But I try to keep the reading light, you know, at the beginning, so that you have time to review some stuff. So which is more stable? Calcium carbonate or calcium sulfate? Are you going to use quantum mechanics to predict it? You could, but we aren't yet. So what clues? Well, properties, right? Depend on structure and composition. So when we think about calcium carbonate versus calcium sulfate, we look at some properties to give us a clue as to which one's a stronger structure. And so what types of properties would we use to give us clues as to which one might be a more stable, more stronger structure? Just properties can be both physical and chemical properties. Just look at physical properties. If physical properties is lattice energies, you know, how much energy it costs to pretty much break all the bonds and vaporize it. Well, we don't have to vaporize it. We just want to break all the bonds. So which one is going to be harder? Which one's going to be easier? And so which one is more stable? We could use some physical properties maybe to determine it. Or we could, you know, this is the two-pronged. This is just using factual evidence, you know, in other words, experimental data. Or we can use some kind of theoretical analysis. Theoretical analysis is this. Sodium chloride versus potassium chloride. Which one do you think is more stable, sodium chloride or potassium chloride, as far as a lattice goes? Crystals. Which crystals are harder to break apart? Sodium chloride crystals or potassium chloride crystals? Well, then add one more thing to this. Do you remember Coulomb's law? Coulomb's law is chapter 2, I think. Somebody remember Coulomb's law? If nobody knows Coulomb's law, I'm going to be very disappointed. Because you know what chemistry is? Chemistry is all about, you know, if I think about the physical forces or the forces of nature, you know, gravitational, is chemistry all about gravity and gravitational forces? Do chemists even care about gravitational forces? Not really. Chemists don't care that much about gravitational forces. I mean, it could impact some things. So what forces of nature are chemists most concerned about? Are they concerned about nuclear forces? Do chemists? No, not really. You know, all of chemistry is 100%. Chemistry is 100% electrical forces. That's all chemistry is about. You know what a dipole-dipole attraction is? It's electrical attraction. You know what an ionic bond is? Electrical attraction. You know what a covalent bond is? It's electrical attraction. These are all electrical attraction. Do you know what Coulomb's law is? It's just as the force of the electrical attraction. You probably know Coulomb's law. Opposite charges attract or repel. Opposite charges attract. Like charges repel. That's Coulomb's law. But Coulomb's law, gets a little deeper. Coulomb's law says the force of attraction or repulsion depends on the charge on body A, the charge on body B, divided by the distance between the center of charges squared. And so, which one's stronger? Well, what's the difference? Sodium ion is bigger or smaller than potassium? Which one's a smaller ion? Potassium or sodium? Sodium ions are a lot smaller than potassium. Chloride's the same. And so the charge is A and B, plus, minus. No difference, but the distance is different between the centers. In fact, I call this the charge density. Sodium has a positive charge concentrated in a smaller volume. Potassium has a positive charge more dispersed because it's a bigger volume, and so it's less concentrated. And so I would call potassium has lower positive charge density, sodium has higher positive charge density. Which one's going to result in a stronger attraction? If you dilute the charge or if you concentrate the charge? Concentrate the charge is going to result in a stronger attraction. And therefore, sodium ions are going to be more strongly held to chloride than potassium ions should be held to iodide. Okay, this is just looking at it strictly from a kind of a what we call point charge point of view. But what we have to do is we have to look at the shape of the charge distribution. That shape of the charge distribution is given by what? The shape of the charge distribution is given by orbitals, right? And so this is why we gotta know orbitals, atomic orbitals, molecular orbitals. We gotta know that. And also how it bonds together. And so if we're looking at this strictly, this is ignoring covalent interactions totally, because covalent interactions can change this. But if we assume 100% ionic, then this is accurate. I expect sodium chloride to be more strong, the lattice. If the lattice is more strong, is it easier to melt or harder to melt? Harder. If the lattice is stronger, it's harder to break it apart. Therefore, you're going to need higher temperatures. If the lattice is stronger, is it more soluble or less soluble? It's less soluble, right? Both of these are soluble, but just based on just breaking apart the lattice, it's going to be easier to break apart potassium. But solubility depends on other factors too, like hydration or solvation of the ions, like in chapter 13 or 14. So we have to worry about other factors too. And so one of the things we could do is just look at the melting point. Which one has a higher melting point, calcium carbonate or calcium sulfate? That could tell us. Or which one's more soluble, calcium carbonate? They're both insoluble, but which one is more insoluble? And so we don't say insoluble. We look at how many grams will actually dissolve in 100 milliliters of water, and determine it that way. And so there are different ways we can do this using factual data. That factual data we don't have memorized, we just look it up. Or we could try to do it theoretically. If we try to do it theoretically, then we look at, a carbonate is a 2-, sulfate's a 2-, calcium's both the same. So which one has a higher charge density? Which one is going to pack more 2-? And sulfate is what we call a spherical ion. Sulfate's tetrahedral. Carbonate is trigonal planar. And so they have different shapes. They'll pack together differently in the lattice. Carbonates, being trigonal planar, aren't going to pack as nicely. So it's most likely sulfate is probably more stable. Just guessing here. And I would expect sulfate to have a higher. But anyway, so we need more information. So this one, we can't really say precipitation is the driving force for this reaction because we don't know which one is more stable, which one's less stable. But we have other driving forces we can look for. What are the other driving forces we can look for? Gas formation. And here we have it. Gas formation is a driving force. And so we could say gas formation. There's one more driving force we look for. What's the one more driving force that we look for? Stronger acid to weaker acid. Because of the conjugate relationship, we only have to look at the acid because the bases will follow the same pattern. And we do have it. We're going from a stronger acid, sulfuric acid, to a weaker acid, carbonic acid, or CO2. CO2 is also considered an acid. CO2 is acidic. And so this is stronger acid, which we call SA. Not, S doesn't stand for strong, it just stands for stronger. Because we don't have, I mean, it could be acetic acid over here. Acetic acid is still stronger than CO2. And so I could attack it with acetic acid. It doesn't have to be attacked by sulfuric acid, right? And so we're going from stronger acid to weaker acid. That's a driving force. Here. So we have two driving forces for this reaction, gas formation and stronger acid to weaker acid. All right, this is what we call the complete equation. So the complete equation is this. We make sure we don't have any unstable, like carbonic. And so this would be the CE, and I have the driving forces listed here. The next thing I need to do is write the IE. For the IE, which is the ionic equation, what I do, or what you'll do is, for the IE, you ionize the strong electrolyte. Actually, do I need to even do this? You guys remember this, right? We've probably done lots of these. I'll do it. Anyway. I'm going to write it up here. Calcium carbonate. Okay, first, what are the strong electrolytes? Okay, you could either memorize individual strong electrolytes, sulfuric acid, hydrochloric acid, sodium hydroxide, et cetera, right? Or you just group those into pattern or category. And so the strong acids are going to be the strong electrolyte. Strong electrolytes are the strong acids. Strong acids, what else are strong electrolytes? Strong bases. I need to put a little asterisk here because I just said don't ionize strong bases. What do we do with strong bases? We hydrolyze. So let's a little note here. Hydrolyze. Don't ionize. And one more. Yeah, the soluble salts. Soluble salts. Salts are just ionic compounds that aren't acids. So calcium carbonate, is that a strong acid? No. Is that a strong base? No. Is that a soluble salt? No. So you'd leave it alone. Sulfuric acid. We have our driving force. Sulfuric acid. So I'm writing the IE here. So calcium carbonate, just leave as calcium carbonate. Sulfuric acid, what do we do with that? It's a strong acid, so we ionize it. I'm not going to hydrolyze it because it just takes too much space. So I ionize it. But what does sulfuric acid ionize into? Does it ionize into 2H plus and an SO4 2 minus? Or does it ionize into an H plus and an HSO4 minus? Yes. Why doesn't it ionize into 2H pluses of a sulfate? It's diprotic, so it's diprotic. Don't you expect both protons to break off if it's diprotic? I'm sorry?
It no longer is an acid.
It's no longer a strong acid. Yeah. Once the first proton breaks off, the protons break off one at a time. They don't break off simultaneously. And so one proton breaks off, and we're left with HSO4 minus. Is HSO4 minus a strong acid? No, it's a weak acid. Weak acids, do they ionize 100%? No. And so we leave the proton on there. So weak acids, we don't ionize. Okay, calcium sulfate is not a strong acid, strong base, or is soluble salt, so we'll leave that alone. Water and CO2 gas. And so this would be the IE. Now the NIE, what do we do? For the NIE, we cancel out the spectators. Are there any spectators here? No. Okay, so the reason we didn't do the first one here, the reason we didn't select that is because HSO4 minus is weak acid, not a strong acid. If HSO4 minus were a strong acid, then go ahead and break off the proton. Here are the three types of electrolytes. You know, we have the strong electrolyte here, weak electrolyte here, and the non-electrolyte here. So a review showing the degree of ionization. Next example I have is potassium sulfide and acetic acid. The potassium sulfide and acetic acid is a hard one. Most of them aren't going to be this hard, I think. But what makes this one a hard one? What makes this one a hard one is because you might have seen something before about this. What's the formula for potassium sulfide? K2S. Acetic acid. Let's use this formula. All right, what should form here? Yeah, potassium acetate, okay. And HS minus or H2S? H2S, because we just take it all the way, and then we'll just balance it. We'll need 2 acetic acids to do this. We'll need 2 potassium acetates here. And then we have a driving force for this reaction. Well, as potassium acetate, potassium salts are all soluble, so that's not the driving force. That's not a gas. H2S is a gas. It's a rotten egg odor gas. Toxic hydrogen sulfide gas. So we have a driving force here. The driving force is gas formation and which one's a stronger acid, H2S or acetic acid? You know, compounds that begin with an H are acidic. So we'll go back. You don't have to have that memorized. So we got the chart here. This chart on tests, you're going to have this chart available. And so you have the chart. You just look it up. Here's H2S. Here's acetic acid. This is the other way of writing acetic acid. This is the condensed molecular formula. CH3COOH. And so it looks like acetic acid is a stronger acid than H2S. There's no leveling effect here, so we don't have to worry about that. Acetic acid is stronger. So what does that mean? That means acetic acid produces more hydronium. H2S produces less hydronium in water. Do we care about that hydronium when we're doing these types of reactions? No. That wasn't hard, was it? So we have gas former and we have stronger acid to going to weaker acid. We have two driving forces for this as well. No precipitation and two driving forces. So what makes that hard? Well, what is the state of acetic acid? Aqueous. What is the state of K2S? Potassium salts are all soluble. Group 1 ammonium salts are all soluble. Potassium is group 1, so it should be aqueous. But what makes this hard is it can't be aqueous. We have to use solid. In other words, what we have to do is we have to sprinkle some solid potassium sulfide into the acetic acid. We can't just grab a bottle of potassium sulfide off the shelf. We are not going to find a bottle of K2SAQ off the shelf. Why can't I just grab a bottle of K2S off the shelf? K2SAQ. I can grab a bottle of K2S solid off the shelf, but I cannot grab a bottle of K2SAQ off the shelf. In fact, a bottle of K2SAQ does not exist. Why? It's too unstable. Why is it too unstable? Because you should know that soluble sulfides are strong. What are the strong bases? Really, you know, if you see it once, you see it twice, probably not enough, huh? You see it once, you see it twice, maybe it doesn't register, you see it like 50 times it will register. So we see sulfide is a powerful base, even stronger than hydroxide. So sulfide is a stronger base than hydroxide. What is the strongest base that can exist in water? What is the strongest base that can exist in water? Hydroxide. Sulfide cannot exist in water. Therefore, I can't make a K2S AQ solution. If I tried to make a K2S solution, do you know what's going to happen? It's no longer going to be K2S. It's going to be if this dissolves in water and I want to figure out what species are in water, what happens is K2S is what we call a soluble salt. So let's write that here. K2S is a soluble salt. Are soluble salts strong electrolytes, weak electrolytes, or non-electrolytes? Strong electrolytes do what? They ionize. So if I have K2S and I put it in water, H2O liquid, what I expect is it's going to ionize into K plus 2 of those, plus a S2 minus, right? And so soluble salt should ionize. Now, I recognize sulfide from earlier. Sulfide is a strong base. Strong bases are strong electrolytes, weak electrolytes, or not electrolytes? Strong electrolytes. Strong bases ionize in water, true or false? No, strong bases hydrolyze. What does hydrolyze mean? Hydrolyze means react with water. So strong bases hydrolyze water to form, well, let's see what it forms. If this is our base and this is our acid, what forms? We're going, okay, now, sorry. For metathesis, we go all the way. This is what we call an acid-base reaction. For acid-base reaction, we only go one proton at a time. And so in this, we don't form H2S, we're going to form HS minus plus OH minus. This is what forms. And so transfer one proton is transferred. Versus metathesis, we transfer complete. Metathesis, do complete. This is not metathesis. This is not a favorable ion combination. This is what we call a Bronsted acid-base reaction. All right, so in aqueous solution, what I'm going to have here is I'm going to form potassium ions, two potassium ions, a HS minus ion plus a OH minus ion. For acetic acid, I wouldn't break that apart, so that just stays together. It's a weak acid. This is a soluble salt, so I'm going to form two potassium ions plus two acetate ions. And H2S is a non-electrolyte, or a weak electrolyte, so we just leave it alone. It depends in the gaseous or the aqueous state. And so the spectators here would be potassiums, so the net ionic reaction would be HS minus plus OH minus. This is what's happening in solution. Yields H2C2 H3O2 plus, goes to two acetates plus H2S. Yeah. This one's screwed up, and so I was going to cancel it because of this, when we dissolve it in water. What are the major species reacting? And this is what we want to see in the net ionic equations. We just want to see what the major species that are reacting, what they are.
For solids, you don't break them down to like the cations and anions, but for that one, you did it because, why did you do it for that one?
All right. Did you notice the difference? Why didn't I do it for calcium carbonate? Why didn't I just break it up into ions for calcium carbonate? Why did I do it for this case but not the previous one? What's the difference? So look at it and tell me what the difference is. Anybody?
Well, this one has a soluble.
Yeah. This one is soluble. The other one was insoluble. So the other one, what's a major species? It's just suspension. It's just a solid slush of calcium carbonate. It could be chunk or whatever. However, this one, when acetic acid what's acetic acid mostly made of? Water. And so when you take some powdered potassium sulfide and drop it into water, it's going to dissolve because all potassium salts are soluble. Well, when it dissolves, does it form potassium ions and sulfide ions? Yes, but the sulfide ions are going to immediately react because sulfide is too powerful of a base to exist in water, and we get this. Does that make sense? Yeah, and so this is a bit more complicated one. If it doesn't make sense, then you need to see more examples and then start making more sense. All right. Let's do another example here. Today's Tuesday. Lead 2 iodide. It's supposed to be Roman numeral 2 here. It should be written lead, Roman numeral 2, iodide. 2 words. And the Roman numeral 2 is right against lead there. Lead 2 iodide. PbI2 plus hydrochloric acid, HCl. PbI2 plus HCl is going to produce a double replacement reaction. What are the products here? Just switch the ions, see if that's a more favorable ion combination. If we switch the ions, and it turns out it's more favorable, then there should be a reaction. If we switch the ions and it's not more favorable, then there should be no reaction. So let's switch the ions, and we're going to get lead with chloride, so we form lead 2 chloride plus hydrogen with iodide, which is just HI. Before I balance this, let's just see if there's any driving force. Is there a driving force for this? Well, it looks like it because we are going to precipitate lead 2 iodide, right? We precipitate lead 2 iodide. Wait, that's a good driving force, correct? But there is a problem with that. What's the problem? PBI2 is also solid. And so this could be like a... So we don't know. Which one do you think is more soluble? Which one's less soluble? Okay, we go with size. This is why you need to know bonding theory. Iodide versus chloride, which one's bigger? Iodide versus chloride. Iodide's bigger, chloride's smaller. So which one's going to have a higher charge density? Chloride. Chloride is going to be more strongly bonded to lead, right? That works great for compounds that are really ionic. But there are some compounds like, you know, lead. Lead 2 chloride is insoluble, but lead 4 chloride is soluble. Why is lead 4? Hey, wait a minute. Lead 2 versus lead 4. Lead 2 versus lead 4. Lead 4 has a much higher charge. Lead 4 has a much higher charge. Shouldn't that be more strongly attracted than lead 2, which has a lower charge? Yes. And so why is lead 4 chloride more soluble? It's because it's not ionic. Lead 4 chloride is covalent. Lead 4 chloride forms molecules. Lead 2 chloride forms lattice, ionic lattice. But it's not 100% one way or the other. Do you guys remember this thing? In chapter 8 or chapter 9, it's been a while since I taught Chem 1A, but it's delta En versus percent ionic character. Do you remember this graph? You know, it wasn't a perfect correlation. It was okay. Delta En stands for the difference in electronegativity, and percent ionic character stands for how ionic is that bond. Because bonds range from 100% ionic to 100% covalent, right? Well, it turns out that heavy metals, you got to be careful because heavy metals will have a lot of covalent character. When we think about covalent character, it's not so simple as looking at charge attractions because what makes a good covalent bond? Tell me what makes a good covalent bond. I'll tell you what makes a great ionic bond. What makes a great ionic bond is high charge density, right? Higher the charge density, that is charge and size. Bigger charge, smaller size, stronger bond. Simple. Ionic bond. What makes a strong covalent bond? What makes a strong covalent bond?
Share electrons.
Well, it's not just sharing electrons. Both HCl and HI share electrons. HCl and HI share electrons. Which one's a stronger bond? Well, they're both sharing electrons, so the bond strength is the same. Size has so it depends on, if you're looking from valence bond, what makes a strong valence bond is good orbital overlap, good atomic orbital overlap. So you want orbitals that are similar in size. For molecular orbital theory, you're looking at LCAO, linear combinations of atomic orbitals. So what makes a good linear combination of atomic orbitals? You want comparable size atomic orbitals so that they can make good molecular orbitals. It's a little bit more complicated than that, but we're going to actually look at it. And so when there's some covalent interaction too, that can screw this up. And since we're dealing with a heavy metal like lead, there's much more covalent bonding character than if we're dealing with something like magnesium. If we're dealing with magnesium iodide versus magnesium chloride, it's a lot easier because this is much more ionic. But when we get to these heavy metals, it becomes more difficult because it's much more covalent. And so here, which one's better? Magnesium chloride. Magnesium chloride is going to have a higher melting point, it's going to be less soluble, etc., because it's got a stronger lattice. But here, the lattice is going to have a lot of covalent, and therefore it's not as easy to predict. So the best thing to do is, rather than approach it from this semi-theoretical point, the best thing is just to look at experimental fact. The experimental fact is which one has a higher melting point. Which one, actually the best one would be which one's more soluble. The one that's more soluble is less stable. The one that's less soluble is more stable. And so which one is less soluble is going to tell you the direction this is going to go. But do you see, we got a question mark here. It's not simple. It's not just a precipitation. Okay? More analysis has to be done. But hopefully there's another driving force so we don't have to deal with this. And so what's the other driving force? Well, it's HCl versus HI. Which one's a stronger acid? HCl versus HI. Now that's simple. HCl versus HI. Looks like HI is a stronger acid, right? If HI is a stronger acid, then we're going from weaker acid, HCl, to a stronger acid. That's the reverse. We should be going stronger to weaker. Therefore, NR. Is that right? Is that right? No, that's wrong. I mean, it's right, but it wasn't fair because I tried to fool you. I tried to trick you because I didn't consider something. I didn't consider what? This is wrong. HCl versus HI, which one's stronger? They're equal, right? Why are they equal? Because of the leveling effect of strong acids. And so we're really stuck here. The only way we can figure out is we need some additional data. My first guess is that chloride is more stable because chloride is smaller. And so let's take a look at the data here. We used to go through these books. We have, when I was a student, if I wanted to look up lead chloride versus lead iodide, I would look in a book called the CRC. The CRC stands for the Chemical Rubber Company, and they published this book called the Handbook of Chemistry and Physics. It's like this thick. And then I'd flip through the pages, right? Or I'd look in the Merck Index. And Merck Index is another handbook. Mostly for organic and biological. The Merck, it's from the drug company, Merck. Flip through that. Those are very useful books, but now a lot of the stuff's online, like Wikipedia. Look it up. All right, so I'm looking at lead 2 chloride. Here's the lattice. This is the three-dimensional lattice using sticks for lead 2 chloride. Well, look at the solubility here. Solubility in water, 10.8 grams per liter at 20 degrees C. Remember that. Solubility of lead 2 chloride, 10.8 grams per liter. Solubility per liter. So this is per 100. So I'll have to multiply this by, if I want it per liter, I'd have to multiply by 10. So multiply, it's 0.75. So 0.75. Lead 2 iodide has a solubility of 0.75 grams per liter. Lead 2 chloride has a solubility of 10.8 grams per liter. Lead 2 chloride is much, much more soluble in water. Lead 2 iodide is much less soluble. That's opposite of what I predicted based on size, because I didn't consider the covalent interaction. I was just looking strictly at the ionic, and I was treating the bond as being purely ionic and not covalent at all. This is why you need to go back and review some bonding theory. So it's there. But anyway, so it turns out that lead 2 iodide is more stable based on solubility than lead 2 chloride. And so this is less soluble. This pen is this is less soluble. This is more soluble. Even though I predicted the opposite based on size. And therefore, we expect the reverse reaction. This should be a better precipitate than that. And therefore, we aren't going to destroy this one to form a weaker precipitate, are we? No, so we expect no reaction. No. Okay. But, you know, are you going to have access to Wikipedia? No, but this is why what you do is, you know, if you're given this on a test and you don't have access to Wikipedia, then you make simple arguments like this. You know, what a lot of people do on tests is they say, I can't answer that. I don't have the data, right? But that's not a good answer, because you're leaving it blank. Blank means, you know, you have no idea how much you know. And so if you're ever given a problem where, oh, I'm missing this number or missing that number, what you do is you try to answer it the best you can. And, you know, if you had to wait until you had the perfect answer for everything, you'd get nowhere. And so what you have to do is you have to, you know, answer it the best you can with the data that you know. And so answering the best you can with the data that you know, you might do an argument like this, based on Coulomb's law back in chapter 2. You know, I'd expect the chloride to exhibit a stronger lattice. And I would argue that, you know, because the chloride should have a stronger lattice, therefore that should be a more stable precipitate, therefore we should have reaction. If you wrote something like that here, you know, that's a perfectly fine answer, you know, except you're missing the covalent interaction, which, well, but that's okay, but you have it answered. That would get a lot more points than saying, oh, not enough data. I don't know, you know, what to do. And so what you do on tests, this is what you do on all the tests, because some of the tests are just really hard, you know, and you just try to answer the best you can. You aren't going to get the perfect answer, right? But you come up with a nice, reasonable answer that shows that you've analyzed the stuff. That's it. And so that's another tool, in test-taking thing like at UCLA that I did quite a lot, you know, because the questions never got the correct answer sometimes. Anyway, I'll stop here, and then I'll see you guys tomorrow.